Hello everyone, welcome to this lecture video tutorial in Calculus 3. Enjoy learning. Hello everyone, in this lecture video we will be discussing about how to estimate the value of a given series. So as you can see here, if you analyze the title of this lecture, um, if you recall our previous lecture video about infinite series, as you can see, uh, what we did is we only show that the series is convergent or not. So actually we didn't show a method on how to find the value of a series. As you can see here, we are going to estimate only the value of a series, um, with the exemption about the geometric series and the telescoping series, where you can find the exact value of the uh, infinite series. All others, as you can see, when we talk about divergence test, uh, theory comparison test, limit comparison test, integral test, um, alternating series test, as you can see, what we did in that in the previous lecture, we only show that the series is convergent or not. So we didn't actually find the value of the series. So that's why in this topic we are going to estimate the value. So the question is how to get the value of a given series. So there are um, applications that you can use uh, on how to get the value of the series, but uh, that topic falls to to what they call this one, to power series, which is in part 2 of our lecture in this chapter. Okay, so when we talk about power series, that's how you are probably how you are going to get the value of a given series. But for now, we will use some apps and assume that the the value of a series is through using that. Okay, so as you have noticed also that since we are uh, as you have noticed also, we are going to estimate the value of a series. So meaning to say that in the assumption of this topic is we are assuming that the series is convergent. Okay, so since we are going to estimate the value of a series, so we are assuming in this topic that the series is convergent. So of course we will be talking about uh, the Kittiet partial sum. Okay, so without further delay, let's uh, discuss how to estimate the value of a given series. So actually uh, we will be using some several tests, three tests that we are going to use on how to get the value of a given series. So to start uh, as I've said before, let's assume that the infinite series summation of a sub n, where your n starts from 1 to infinity. It doesn't matter if it starts with 1. There are series that it will not start from 1, as I've discussed before. So let's assume that this series converges to the sum t. Okay, so what does this mean? If you recall uh, our previous topic, the definition of the convergence of a series, this means that uh, if we take, this is in relation to the partial sum. Okay, if you recall our lesson number 3, if we take the partial sum remember this notation, t sub n summation of a sub I, where your I starts from 1 up to n. Okay, if we take this partial sum, then this will form a convergence sequence. This is just like our discussion before, and its limit is t, rt here above. Okay, so what does this mean further? That is the limit of our sequence of partial sum as n approaches to positive infinity is equal to t. Okay, so let's move up. So the question here is, okay, this is the question. What is the meaning of the discussion above? With respect to our title is to estimate the value of a given series. Okay, so the answer, okay, let's wait for the program to respond. So this is the answer. Notice that since the limit converges, this means that we can take the partial sums t sub n as this is the, as you can see in your calculus 1, the meaning of the limit. This means that we can take the partial sums t sub n uh, as close to t to the sum t as we want, as we want by taking n large enough. So this is the, as you can see, as you recall, the meaning of the limit. So this means that this means that the what do you call this one, the sum of the actual value of the series is can be approximated by the sequence of partial sum. And of course, if n becomes larger and larger, or big enough, like your n is 1000 or 1 million or 10 million, uh, you will see that the actual sum of the series is close enough to the n partial sum, t sub n. So this means that uh, this is a method, or one method of estimating the value of a series. Okay, so this is one method of estimating sorry estimating. So what are we going to do is just look at the sequence of partial sum. And uh, as I've said before that uh, with respect to the geometric and the telescoping sums, we can, as you can see, we can get the actual sum of that series. But other than that, other series like the one we use in uh, convergent direct comparison test, limit comparison test, integral test, alternating series test, and many other tests, uh, we cannot get the actual value of the sum of the given series. Okay, so please remember that. So that's why we in this topic we are going to estimate the value of a given series, the value of a series. Okay, so with respect to this method of estimating the given series using the n partial sum, so the question now is how good is this estimation? Okay, so how good is the n partial sum in estimating the actual sum of the given series? Okay, and secondly, the second question is can we make the estimate better? Okay, so let's wait for the this question here, question with respect to q1. How good, how good uh, is the estimation? Okay. Second question is there any way to make the estimation let's move up. Okay, let's wait again for the program to respond. So maybe we can, so please as you wait for the program, just imagine this question. Okay, how good is the estimation, uh, and is there any way to make the estimation better? Okay, better. Okay, so to answer the first question, let's use another color here. To answer the first question, uh, let's start with the original series. Okay, so uh, let's start the discussion with the full series. And strip out the first n terms. Okay, so as you can see here, let's move again. Let's wait for the program to respond. So what do we mean by the full series? Let's move upward. Okay, this is the series. A sub I, so this is the full series. Okay, so what do we mean by strip out the first n terms? So we have to dissect, or we have to, I don't know if that's the right word, but just look at this sorry, let's look at this to call this one notation here. This should be a sub I. Can I erase this? Okay, let's wait for the program to respond. This one. Okay, let's wait again. A sub I. So from here, it starts from n plus 1 to positive infinity. So why? So remember that we separate this the left hand side. So this is the full term, the full series. So we start from I, from 1 to n, and then this second series here is will start from n plus 1 up to positive infinity. So notice that this the first term on the left hand side, okay, this one here, the first this first term on the left hand side, no, not left hand side, the right hand side. So this is our left hand side, this is our right hand side. So the first term on the left, the right hand side, this is the, actually this is the end partial sum. Okay, you can write it this way. This is our t sub n. Okay, and this term here on the right hand side, we will denote this by r sub n. Okay, and this term here is the r sub n here is what we call the remainder or the error. And we know that we assume that the series is convergent. So this series here on the left hand side converges to t. This will not work if the series is not convergent, so please remember that. Okay, so uh, finally, this difference here, so after, so we can rearrange this. We can write this one as r sub n, which is equal to t minus t sub n. Okay, can transpose t sub n on the left hand side and then use symmetric property. Okay, so r sub n is what we call the error. Okay, the error, and this is what we call the end partial sum, and this is the sum of the series. Okay, so can we use another color here? Maybe can use the color purple. Okay, let's wait for the program to respond. So this remainder here is the difference between the exact value of the series and the value of the partial sum. Okay, and then we will be using this one as a estimation of the we will using this idea here as an estimation of the value of the series. Okay, so what happened, this one is what we call the what happened, this is what we call the error. Okay, error. This one is what we call the end partial sum, and this one here is what we call the exact value or the actual value, exact value of the series. Okay, so please do remember that, let's move up. Okay, please do remember that we cannot get our hands to the actual value of the remainder because we don't have the actual value of the given series. Okay, so to get the actual value, we can it is beyond of the in this topic. In our previous topic also, we don't discuss that. So as I've said, we can get the actual value of the given series using a calculator, maybe online calculator, or like Mathematica, like Mapo, or using other online calculator. Okay, and also we can use the idea of the power series, which will be in the next part of our discussion. Okay, power series, Taylor series, Maclaurin series, and so on and so forth. But since that topic is uh, will be discussed in the part 2. Okay, so what we will do here is we will use the online calculator, okay, to get our hands into the exact value of the series. And so since we don't have the actual value of the uh, the series, and we assume that the series is convergent, we can use some of the tests that we've got so far uh, for convergence to get the a pretty good estimate of the remainder, provided that we have some assumptions of the series. The convergence that I talk here is the um, the direct comparison test, the limit comparison test, integral test, alternating series test, and so on and so forth. Okay. Once we've got the estimate of the value of the remainder, we'll also have an idea on how good a job the partial sum does to estimating the actual value of the given series. And uh, that the test that we are going to use to estimate the remainder uh, in this discussion is the integral test, the comparison test, the alternating series test, and probably later the ratio test or the root test. Okay, so please do remember of that though. So the alternating series remainder will be we will be discussing that one later. So let's move the other side here. uh, Maybe this one. Okay. uh, Several tests, several tests, several tests uh, uh, that we will use to get estimates, estimates of, can we move this one on the of the remainder. Okay, the remainder is what we call the error. Okay, so one, we will use the first is the integral test. Integral test. Okay, so remember that as I've said before, we will have a preconditions of the given test that we were going to use. For example, in the integral test, we know that the preconditions for this for this test is that the test must be continuous. No, the test, the a sub n, which will be denoted as f of n, remember that in our previous discussion, is continuous, decreasing, and positive valued. Okay, so please do remember of those preconditions. For the direct comparison test, we have a condition for that. For the alternating series test, we also have the conditions, those conditions. So for this test, uh, we will use the integral test to get a good estimate of the remainder. So first is we have to assume, uh, I will not write here anymore, uh, or maybe this one, okay, this one na lang. Okay, we will use, we have to let, uh, sorry, okay, that one, f of n to be our a sub n, and assume that f of n is decreasing. It's a decreasing function, positive valued, and what are the other conditions, and continuous, continuous function. Okay, and then we will use this idea to what we call this one, to estimate the remainder. So let's recall first. Let's recall that the remainder, that the remainder is this one. This is our remainder. A sub I starts from n plus 1 to positive infinity. Okay, this is our remainder. So if you try to expand this, I know this is very common to all of you. So this is the remainder. Now if we start at x is equal to n plus 1, this one here, and we take the rectangles of with 1 and use the left endpoint as the height of the rectangle, we can estimate the area under the function f of n or f of x on the interval n plus 1 up to positive infinity. Then we can estimate the remainder. Okay, so let's try to put that into writing. Now consider the figure below. Okay, so I will have to, the one that I've said before, I will try to make a diagram for that, or a figure. Okay, so notice that in this figure, uh, we overestimate the exact area of the remainder. Okay, remember that there are shaded region here outside, below, no, above the graph of the function. Okay, so what we can conclude here is that we overestimate the area of the remainder. Okay, so what we will do here is that uh, we have this following inequality. Okay, so maybe let's use this color here, this one. This area here, as you can see, is this one, that one. Okay, that area here above the graph is not included in the, what they call this one, in the area under the curve, when you start at the point n plus 1 up to positive infinity. Okay, so actually we overestimate the exact area. Okay, so this implies that the r sub n, okay, you can have this inequality. So remember that this is our function f of x. We know in our calculus 1 subject, this is the area is represented by this one, integral of where n starts from n plus 1, where your lower limit starts from n plus 1. Okay, why is this? We can see in the graph that the remainder r sub n, the area estimation you can see the graph that the remainder r sub n, the area estimation, will overestimate uh, estimate the exact area. Okay, we can see the graph, this one graph above, that the remainder r sub n, this one below the graph, the area estimation will overestimate the area. So that's why we have this what they call this one, this inequality. Okay, now do the same with the other one. Okay, so you start at x is equal to n, and then get the width. Remember that the width is 1. N plus 1 minus n plus 2 minus n plus 1 is 1. N plus 3 minus n plus 2 is 1 again. Okay, so the width of this area here is 1, but the height is the left end point. Do the same with the other, the same with 1, and then this time the height is the right end point. So what you will do is to start at x is equal to n. So maybe we can use this lasso effect here. So let's wait for the program to respond. Of this graph. Okay, so here next we do the same analogy as the one discussed above. Okay, so but in this figure and this diagram, it is opposite to the to the graph above. Instead, it says in the previous discussion, the previous graph, the area will be overestimated, but here the area is underestimated. Okay, so do the same, copy here this one, but again your conclusion uh, must be in opposite of this inequality here. Okay, so can we move up? That one. Okay, so please do remember that the area of the remainder r sub n will underestimate. Okay, the estimation of that area will underestimate the exact area. Okay, so that would be your conclusion. That one. So this implies that the remainder will underestimate. Okay, start with n up to positive infinity. Okay, so your conclusion here is the what they call this one, uh, the area the area in this case this case the uh, the area estimation estimation will underestimate under estimate estimate uh, the area. Okay, in this case the area estimation will underestimate the area. Okay, that's the difference between the two graphs. Okay, so what shall we do here with that sorry with that result? So let's move up. I'm so excited to probably get the estimate. Okay, so here uh, combining the inequality inequalities, sorry, combining the inequalities above, we have we get integral of f of x dx, where the starting point is n plus 1 up to positive infinity. So just analyze. Okay, this is the inequality if you combine the inequalities above. So now recall our previous discussion. Remember this one. Recall as no remember our previous discussion, not that one, this equality. Did you remember this one? Plus r sub n. Okay, remember that inequality. So this implies that if remember this also this inequality in the first graph, okay, n plus 1 to positive infinity f of x dx. Okay, let's wait for the again for the program to respond. So what we will do here to use this equality, we will add both sides by t sub n. Okay, if we add both sides by t sub n, so what will happen? Sorry again, I'm sorry, this integral, so I'm used to write the summation symbol. T sub n are positive. This is notice that the terms of the integral test topic are positive valued.
Okay, so please to remember that this is positive. If we add both sides by t sub n, the inequality will not be reversed. Okay, positive infinity, and notice that this is t. Okay, sorry again, that one, sorry, so it's not good. Maybe so t sub n plus this one, and you can do the same for the other one. Okay, so this is t. Okay, also if you have this one r sub n less than negative, that one, not negative. Okay, if you add both sides by t sub n, okay, dx, this is our t here. So combining again, uh, we will get, sorry, combining these two, this one, this inequality and this inequality also, what we will get is, let's move up, combining together, combining together, sorry, we have, or we have uh, t sub n f of x dx, which is less than or equal to t, less than or equal to t sub n plus n positive infinity f of x dx. So this is now our estimate of the uh, sum of the series, which is denoted by t. Okay, so let's have an example here. So can I put a box here? Okay, that one. So as an example, using n is equal to, let's say, 20. Okay, to estimate the value of this series, summation of 1 over n cube, where n starts from 1 to positive infinity. This is we know that this is a p series. Okay, and rp is 3, so therefore this is convergent. Okay, so this converges to a sum p. Okay, so we will use our method before. So this is the solution. Okay, this is the solution. Okay, first For comparison purposes, the actual value of the given series is, as you can see here, sorry, and starts from 1 to positive infinity, is equal to, remember that we didn't compute this by hand. What we do is to use a program, so, or a website. As you notice here, I use Wolfram Alpha to get the um, actual value, or the exact value of the series 1 over n cube, where n starts from 1 to positive infinity. So as I compute it in this website, okay, this is the sum, okay, this one. But as you can see, there's no uh, decimal value for this. So all you have to do is to click this button here. So if you click this button here, you will see a value here. So the decimal approximation is this one. Okay, so if we round off to 10 decimal digits, we will have this one, 1.2020 56903. Okay, ten decimal digits. Okay, so round off to 10 decimal digits, and then after this, sorry, this is not greater than, this must be equal. So I guess I have to, okay, let's wait for the program to respond. Here, let's use an eraser here. So using n, which is equal to 20, we will use the n partial sum. Okay, not, maybe I will not use n is equal to 20, maybe less. Let's say n is equal to 10. Okay, let's have, okay, n is equal to 10. Let's wait for the program to respond. So here, using n is equal to 10, so we will compute the 10th partial sum, as you can see below. So summation t sub n, t sub, sorry, this is t sub 10, summation of 1 over n cube, and sorry, this is not I cube, and not n, I is equal to 1 to 10. Again, if you use the Wolfram website, replace this to n is equal to 10, the n value, and then compute again. The value is this one. This is the decimal. No, not the decimal, this is the fractional form. So let's compute the decimal form, 1 up to 10. Okay, so the decimal form is this one, 1.19. so let's have 10 digits. Okay, so 1.19753191, 1 2 3 4 5 6 7 8, 2 more, 985 or 86. So this is 10 decimal digits. Okay, so let's move up. Okay, please take note that in some sense that the actual value, as you can see here, is close, in some sense close to this 10th partial sum. Okay, so 1.1975, and then we have 1.2020. Okay, but as you can see, this is really not close either. Okay, so for now, let's compute the let's compute the integrals. As you can see on our previous discussion, the integrals, and we know that these integrals are easy to handle. Okay, now let's compute the integrals as we see below. So the integral 10, we have 10, n is equal to 10, 10 to positive infinity 1 over x cubed dx. This is very familiar. 10 to b x to the negative 3 dx. B approaches, this is improper integrals. If you remember your previous subject in calculus 2, so this is the limit of x to the negative 2 over negative 2 evaluated from 10 to b. Your b approaches to positive infinity. So this is the limit of negative x to the negative 2 negative, sorry, this is again, let's wait for the program to respond. substitute our x to be this variable here, b. So this is 1 b to the negative 2 over 2 minus, we have plus 10 to the negative 2 over 2 as p approaches to positive infinity. And if you evaluate this one, this is of course 0. Okay, you can p to the negative 2 is negative 1 over 2b squared, and as you can see, as b approaches to positive infinity, this becomes 0. So what remains here is this one. So this is 1 over 10 square, which is 100, times 2 is 200, so 1 over 200. Okay, so let's wait again for the program to respond. Let's choose this color. Okay, what happened? Okay, this is 1 over 200. And for the other one, and the integral of 11 to the positive infinity, 1 over x cubed dx. This will become the limit of the integral 11 to the b as b approaches to positive infinity, x to the negative 3. So this is just the same as this one. So let's proceed to this form. This is limit of negative 10, no, negative b to the negative 2 over 2 plus 11 to the negative 2 over 2 as b approaches to positive infinity. And as you can see here, this is 0. Okay, so 11 squared is 100. 11 squared, let's compute it. 121. Okay, let's try this color here. We have 0 and go back again to blue. This is 1 over, sorry, yes, that one, 121 times 2, 121 times 2, 242. This is 242. Okay, so that's how you are going to get the integral. Okay, so remember, before using this method of estimating the sum of the series, be careful that the integral the integrand must satisfy the integral test, the assumption in the integral test. Okay, so plugging this one, plugging this gives us in the box above, just plug in the value. Okay, so remember, let's can we move up? Okay, we have t sub n plus the integral of f of x dx. okay, where the lower limit starts to n plus 1 up to positive infinity. Okay, so anyway, just recall the box above. So okay, I will recall it here. Recall something, this is something like t sub n plus the integral of f of x dx evaluated from n plus 1 to positive infinity, t less than t sub n plus this one f of x dx. So this is what's inside the box. So plug in. So our n is 10. So t sub n, t sub 10 is as you can see, this is 1.1975 31986 plus 1 over n plus 1. This one integral here we have 11. So this is 11 to positive infinity. This is 1 over 242 less than or equal to t less than or equal to 1.1975 31986 plus, so this is our 10 here is 10 to positive infinity. This is 1 over 200. Okay, and if you simplify this, you will get, this is the bound of our actual sum. Okay, so get the value of this one first, okay, using your calculator. Okay, so as you can see here, we will use the small scientific calculator. So let's compute the left hand side first. 1 point this one 1.1975 86 plus 1 over 242. 1 divided by 242. So this is the value, 1.201. Okay, 1.201 6642 6642 17 17. And on the right hand side, so let's copy this, control copy, paste, and this is over 200. So this is 1.202 5319 86 86. Okay, so if you recall the actual value of the sum, the sum of the series, this is as you can see, if you recall, this is 1.20205690t. Okay, approximate to 10 decimal digits. Okay, so as you can see here clearly, this actual value is between this lower bound and upper bound. So both the upper bound and lower bound are now very close uh, to the actual value. And if we take the average uh, of the two, we get the following estimate of the actual value. Okay, so get the average of these two. So just take a sum and then divide it by 2. Okay, so just get this sum here, copy this one, put a plus copy divided by 2. So the answer is 1.202. 1.20209 0.2029 8120 8120. So as you can see, this is pretty much close to the actual value. Okay, so let's move up. That is pretty close to the actual value. Okay, so that's how you are going to estimate the sum of the series using the integral test. Okay, so it depends upon the value of n, or the n partial sum. So we have 1.2056 and here we have 1.202098120. This is pretty close to the actual value. Okay, so for our second test, okay, just wait a little while. Okay, in this case, we will use the comparison test to estimate the value of the given series. In this case, I repeat, unlike the integral test, we may or may not be able to get the idea of how good a particular partial sum will be as an estimate of the exact value of the series. Okay, much of this will depend on how the comparison test is used. So remember that in the comparison test, the b sub n that you are going to compare to the actual series or to the given series will depend on the value, on how to estimate the given series. Okay, so please remember that. So first, let's choose another color here. First, let's remind ourselves uh, ourselves uh, on how the uh, comparison test or direct comparison test uh, actually works. Okay. Notice that if you are given a series, okay, you are given a series summation of a sub n starts from 1 to positive infinity. uh, let's assume uh, that we've used the comparison test to show that uh, it is convergent. Okay, therefore we've found we found, remember our previous discussion, a secant series. Okay, series summation of b sub n, where n starts from 1 to positive infinity, that converges. Okay, remember, not the other one, the direct comparison or comparison test theorem number 2, which talks about divergence. And also we note that a sub n must be less than or equal to b sub n for all n. Okay, and also recall that our b sub n, no? That both a sub n and b sub n are positive for all n. Okay, so let's wait for the program to respond again. Okay, both a sub n and b sub n are positive for all n. Okay, and then in the previous discussion we want to know how good a job the partial sum is in estimating the actual value of the given series. Okay, so our goal here, again, before, I think we have an internet connection, so I guess we have. So let's put our goal here. Our goal, can we have another caller? Let's move up, maybe. Okay, can we move up? Our goal here is what we want to know, how how good the of a job the partial sum, this one, p sub n summation of p sub I starts from 1 to n. We want to know how good a job the partial sum p sub n will be in estimating the actual value of the series, this one, starts from 1 to positive infinity. Okay, again we will be going to the idea about the remainder. Okay, the remainder of the series, and we denote it last time using the notation r sub n. Okay, r sub n. So let's move up. So here we will use the remainder r sub n to do this. Okay, so remember that we have two series here. So the series a sub I and the series a sub n and the series b sub n. So actually we have two remainders here. Okay, so let's write down the remainder for both series. So I think we have to erase this one first. Okay, and we know that these are again, let's wait for the program to respond. Let's wait. So I have an eraser here. Let's erase this one first. Okay, and then the remainder for the series a sub n is this one. What happened? Let's wait for the program to respond again. A sub I starts from 1 to n. So this one corresponds to the series a sub n. and URST. U. Let's try this one. U sub n, summation of p sub I, where I starts from 1 to n. Sorry, this is the remainder, so this one is, sorry, up to positive infinity. Again, we have to wait. Okay, that one. Okay, notice also, that since our a sub n is less than b sub n, uh, we know that uh, r sub n, this is obvious, it's less than or equal uh, to u sub n. Okay, that's a fairly obvious situation. Okay, and before we go through the example, I will put a reminder here about the comparison test. So let's move up. Again, let's wait for the program to respond. Okay, let's move up. Let's have a reminder here. Reminder. I know that you observe this when using the comparison test. Comparison test, it is often the case that the b sub n's are, or the p sub n, sorry, that the b sub n are fairly simple, and have a nice terms. Okay, terms, and for that, and let's wait for the eraser. Can we erase this one? Can we erase this? The b sub n are fairly simple and have a nice term, and we might actually be able to get an idea on the size of t sub n. So for instance, if you have a p series. Okay, so if you have a p series, uh, we can use, if you have a p series, uh, this refers to b sub n. Okay, refers to b sub n. If you have a p series, we can use the result, use the results from above to get the upper bound, to get the upper bound uh, on p sub n as follows. So you can have this, let's have this color here. Okay, r sub n is u sub n, which is less than or equal to integral of course where g of n is equal to b sub n. Okay, so that's how you are going to estimate if the uh, series that you are going to compare is a p series. But if your series is a geometric series, okay, so what will happen if if the series that you compare, so the b sub n is a geometric series, then we can compute the u sub n exactly. Okay, so here if you have a geometric series, then we will be able to compute u sub n exactly. Okay, so however, let's move up. However, if we are unable we are unable uh, to get the idea of the size of u sub n, then using the comparison test, to help with estimates, won't do uh, as much good. Okay, so please remember these things. So let's have an example here. Example, so using n which is equal to 10, estimate the value of the series summation of 1 over, sorry, let's wait again for the program to respond. Let's wait. Okay, 1 over n factorial. Will our n starts n is equal to 2 to positive infinity. Okay, so this is our solution. Okay, so this is our series I guess before, and we know that what is the b sub n. Okay, that we compare last time in I guess in lesson number 3, maybe lesson number 3. So just recall. Okay, this is our solution. So based on our previous discussion, okay, the second series, this is our b sub n, is just recall, just look at your notebook. This is compared to 1 over 2 to the n minus 1. N is equal to 2 to positive infinity. And we know that this series converges to 1. Okay, so again our n here is 10. So using n is equal to 10, the 10th partial sum is 1 over n factorial, and starts from 2 to 10, which is equal to again, if you use this calculator, where's that one, this one, 1 over n factorial starts from 2 to 10. Okay, just wait, and but this is the decimal approximation, 718,281,828. Okay, 718 0.718 281 828 281 828 1 2 3 4 5 6 7 8 9. Let's add more. 8. We have 5. Okay, so this is the 10th partial sum. Let's move up. So let's wait for the program to respond. So how good is it? Just like in the previous example. Let's move up. Okay, so how good is it? Okay, so we'll know that R sub 10 is less than or equal to U sub 10. And notice that our second series is a geometric series. So you just look at the reminder above in the previous discussion. If it is a geometric series, then what will happen is you will have to use directly. Okay, so this is 1 over 2 to the n minus 1. Your n starts from 11 to positive infinity will be the upper bound. For the error between the actual value and the estimate, and this is summation of 1 over 2 to the n minus 1 more than to positive infinity will be the upper bound. For the error between the actual value and the estimate. Okay, so since our second series is a geometric, okay, let's wait for the program to respond. Okay, let's move up. Is a geometric series. We can compute directly as follows. So as you can see here, uh, this is a geometric series. Just like before, we have summation of 1 over 2 to the n minus 1, and starts from 2 to positive infinity, and we strip out the terms starting from 2 to 10, and then until comes 11 to positive infinity, 2 to the n minus 1. Okay, so rearranging, this becomes summation of 1 over 2 to the n minus 1, and starts from 11 to positive infinity. This will become summation of 1 over 2 to the n minus 1. So this is, sorry, this one goes here, okay. So n starts from 2 to positive infinity, minus we have summation of 1 over 2 to the n minus 1, and starts from 2 to 10. So we know that this one converges to 1 by our previous discussion, and if you get the sum of this using your calculator or using Wolfram Alpha, as you can see here, this is 511 over 512. Okay, so we have a mosquito somewhere. This is 1 over 512, or this is equal to 0.00195 and 3125. Okay, so let's move up. So again, let's wait. So according to this, if we use t, which is in our previous calculation, but as you can see in our previous calculation, we have 0. Okay, sorry, this is not 20, this should be 10. Okay, that's why I made a mistake. 718281, 718281, 8011. So this must be 0.7182818011. So let's move upward to change the answer of our 10th partial sum. this one here. Okay, this one here is wrong. This is 0.718281 281 8011. Okay, so according to this, if we use t, which is approximately, this is our end partial sum. Okay,
So according to this, if we use t, which is equal to approximately equal to 0.718818011,
as our estimate of the actual value, we will be off from the exact value by no more than 0.001953125. Okay, and we know that that's not too bad. Okay, so in this case it can be shown that again, if you will use our online calculator to positive infinity, we know that this is equal to e minus 2, which is if you use the decimal value, this is 718281 8285. Okay, and then and so we can see that the actual error in our estimation is this is our error, r sub n. This is the actual value minus the estimate. So the actual value, which is 0. As you can see here, 718, this one, 281, 8285, minus the estimate, which is this one, 718, 281, 8011, this is 0 0.000 1 2 3 4 5 6 7 274. Okay, which is of course this is lesser than 0.001953125. But remember, there are times when the this value here, the error is equal to this one, but mostly this is less than. Okay, this error here. Okay, that's how you are going to use the comparison test to show that the how you are going to estimate the value of the series. Okay, so of course it will be it matters on the b sub n that you are going to use. Okay, so our third method, our third test is the we will be using the alternating series test. So of course this test will be used if there is a negative terms, but the negative terms that we are use here is should alternate. Okay, you cannot use this if the given series is not an alternating series. So this estimates this method or this test will be used to estimate an alternating series. Okay, but if any other series, so just use the integral if it fits the what they call this one, the assumption, and also you can use the comparison test if it's fits the assumption. Okay, so let's move to our third test. Okay, this third method that we use to estimate the value of the series, we will be using the alternating series test. We know that in the previous discussion the terms contain only a positive value. Okay, your a sub n must be greater than 0. So what will happen if we allow negative terms? So actually this will be difficult, but there is one exception in which we can estimate the sum of a series that involves negative terms, and that is as you can see in the title, we will be referring to alternating series. Okay, so once again we will start with a convergent. Okay, we will start with the convergent alternating series, and since we know we will start at a convergent alternating series summation of -1 to the n times a sub n, where n starts from 1 to positive infinity, or this notation, to the n plus 1 to positive infinity. Okay, we will start at the convergent alternating series which in this case, which in this case uh, case that it happens, since it is a convergent alternating series happens to satisfy the condition for alternating series test. Okay, so meaning our a sub n is greater than or equal to 0, meaning it's positive and decreasing for all n. Okay, and also we note that in this discussion we will be using this one. Okay, I'm sorry, there's an ant in my eyeglass. Okay, we will be using this notation. Okay, so again, we can wait for let's wait for the program to okay. Notice that we have two notation here. So in this discussion we will be using this notation. Okay, that one. And then as with the previous discussion, we want to know how good an estimation of the actual series value with the partial sum s t sub n b. And also we want to know that in the previous discussion that the remainder r sub n, and we know that the r sub n is the error in the estimation, and so we want and so if we can handle on that, we will know approximately how good the estimation is. Okay, so please remember that. So from here, review just review the proof of the alternating series test, probably in the book Lighthold. Okay, Lighthold or Larson. Okay, so just review review the proof of AST, and then we can see that the sum t will lie between the end partial sum t sub n and t sub n plus 1. Okay, for any n, and so we have this inequality. Okay, our series, alternating series which converges to t, will satisfy this inequality. Okay, t sub n plus 1 minus t sub n, which is equal to a sub n plus 1. Okay, so therefore we have this inequality. We know that this is r sub n. Okay, which is equal to uh, t minus t sub n. Okay, which is less than or equal to b sub n plus 1. So what we do here is we simplify this above inequality to get this. But anyway, this is just a direct result of this inequality here. Okay, so as you can see, we need these absolute value bars because we don't know ahead of time if the estimation is larger or smaller than the actual value, and we know that the b sub n's are positive. Okay, so please remember that. Okay, so let's have an example here. Let's wait. Okay, example, using n which is equal to 15, estimate the value of summation of -1 to the n plus 1 1 over n squared. N starts from 1 to positive infinity. Okay, this is the solution. So before I am going to what they call this one, before I am going to answer this, I made a what they call this one, I've made there's a mosquito. Anyway, let's wait for the program. I made something before, a theorem about the, with respect to the what you call this one, the alternating series test. Okay, on how to estimate the alternating series. That result is what we call the, okay, I got a mosquito somewhere. That's called the alternating series remainder. Okay, so let's move. I guess I put it down here somewhere. This one. Where's that one? Maybe this one. Yes, this one. Okay. Maybe I could resize it. This one. Just like in the previous discussion, the remainder is denoted by r sub k here. Okay, we discussed this before. If we strip out the n terms, okay, the n terms of this series 1 up to n, and then start from n plus 1 to positive infinity, then we will get this remainder. Okay, because our series converges to t, and T sub k is our kth partial sum, or the nth if you use n. R sub k is the remainder. So this is the theorem for the alternating series. These two notations here are notations for the alternating series which satisfy the conditions for the AST. Then R sub k here is the remainder obtained by approximating the sum of the series by the sum of the first k terms, as you can see here. So this is just the same as in the what I've written before. Okay, so let's move to the solution. Okay, so just wait, we have a mosquito somewhere. Where's our, is this one? Okay, this is the one. Okay, this is what I've told you in the previous slide. Okay, here we use n, but there we use k. It's just the same. It depends upon the notation. Okay, so we are going to use n is equal to 15 to estimate the value of this series. Okay, so we know that this is an alternating series, very clear, and this is convergent. Okay, why? Because this is decreasing. If this is our a sub n, this is decreasing, and clearly the limit of 1 over n squared is 0. Okay, so this is clearly this is clearly an alternating series which is convergent. Okay, for comparison purposes, the exact value is known to be this one, negative 1 to the n plus 1, 1 over n squared. This is pi squared over 12, which is 0.822 467 0336. Just use the calculator. Okay, so using n is equal to 15, the 15th partial sum is given by this one, t sub 15 summation of negative 1 to the n plus 1, 1 over n squared, 1 to, sorry, this must be I. Okay, so I guess, sorry for my kids. Let's go back and let's put this I squared where I starts from 1 to 15, t sub 15. Okay, which is equal to if we use our Wolfram Mathematica, this one, so this is 1 over n squared, 1 over n squared, starting from 1 to 15, and then we should have somewhere here negative 1 to the to the n plus 1. N plus 1 times, we have times here. Okay, so let's evaluate and wait. Okay, wait. Okay, so this is the value. Am I right? Okay, so this is 82, 45, 41. 82, 45, 41. 0.82, 45, 41. 75, 73. 75, 83. 1 2 3 4 5 6 7 8 9 10. 1 2 3 4 5 6 7 8 9 10. So we have 83, 83, 83. Sorry. 75, 75, 74. So this must be 74. Okay. Okay, let's wait. This is 74. Okay. Let's move this one upward. Okay. From the fact above, from the facts or facts above, we know that r sub 15 is equal to our s is this one, 0. This is t minus t sub n, which is less than or equal to a sub 16. Okay, which is our 16 term is 1 over 16 squared. Okay, which is 0.000390625. Okay, so that's the value. Just use your calculator. Okay, so our estimation will have an error of no more than 0.003900625. Okay, in this case the exact value is known. We know that already, and so the actual error and so the actual error is given by this one, r sub 15. Our t is that one, 0.82246703336 minus our t sub n, this one, t sub 15. So this is 15. Sorry. Okay, remember that this is 15. This one. This is t sub 15. Okay. I will correct that one later. 0.82 45 41 75 74. So if you use this calculator, our online calculator here. Clear. Our calculator is 822.822, 0.822 467 0336 0336 minus 0.8245 8245 4175 4175 74. Okay, so this is the answer is 0.002 0.002 0747 0747 23. Okay, so this is the actual error. Okay, as you can see, they are not much of course this one is lesser than this one. Okay, so which is correct based on our discussion. Okay, so I will correct this one. May I erase this? So let's wait. So maybe after discussing the ratio test, we will use that test also to estimate the value of the given series. But for now, since we did not discuss the ratio test, we will not we cannot able to use the ratio test as an estimation for the given series. Okay, so this is this sorry, this is this 15. Okay, okay, if you try to expand this expression here, this inequality here, as you can see in your algebra, so this is equivalent to let's try to explain this more. This is less than 0.00390625. Okay, so that's what we mean by this inequality. So however, if you try to expand this, this is equivalent to negative 0.00390625 less than or equal to t minus t sub 50 is less than 0.00390625. Okay, and then this will become negative, this will become t sub 15 minus 0.00390625, which is less than or equal to t, less than or equal to t sub 15 plus 0.00300625. So plug in the value of t sub 15, which is, as we know, This is 0.00, no, this is 0.82. This is 0.8 uh 245 minus 0.003 less than or equal to t, less than or equal to 0.824541 plus 0.00397 390625. So then use your calculator to get the sum. This is 0.828 4480074 on the left side. This is 0.8206 355,074. Okay, so our sum, if you recall the sum t in your notebook, so maybe you write this, the value of our t, you will see that it is between in this interval. Okay, so that's how you are going to know if you this is the estimate. Okay, and so since the value of t is we assume that we do not know this, but we know that the series is convergent, and since we use sum up application, web application, to determine the sum of the series, then we can verify that it is really between this interval. Okay, so I hope that this is now clear, and as you can see that the error, as I've discussed before, the error is the actual error will be less than the estimated error. Okay, that will be always the case. And remember that the error is the only upper bound for the actual error. Okay, so what is the actual error in the discussion? So the actual error is what? So can we move now? Okay, so this is the actual error. Okay, so this is the estimated error. As you can see, this is bigger than the actual error, so that will be the case. Okay, for your assignment, we have 6 problems here. So all you have to do is just like before, just wait for the instruction. You can solve this, but you can wait for the instruction in the Google Classroom on how to upload your solutions for your assignment. Okay, so thank you so much for listening. Our next topic for the, I guess, the last part of part 1, the last topic for part 1 is the ratio test and the root test, and also the absolute convergence and the conditionally convergence. So thank you so much for listening. If you are not yet a subscriber, just click that subscribe button and bell button down below for instant notification